Welcome everyone. This is Arjun here from QuantInsti, and good morning, good afternoon, and a good evening to all our participants and attendees from across the globe. We would be starting the webinar on machine learning and quantitative finance, and it's going to be taken today by Mr. Eric Hamer, who's the CTO of Quantiacs. Now, talking about the webinar and QuantInsti, my name is Arjun Sharma, and I am handling international sales with QuantInsti. QuantInsti is an institute which deals with courses in algorithmic trading, and recently we've associated with Quantiacs. Now, Quantiacs and QuantInsti have teamed up basically to accelerate the transformation of quantitative finance and algorithmic trading education. Now, talking about how we are going to help people out with the education, the partnership will combine QuantInsti's expertise in professional quant training and algorithmic trading education programs with Quantiacs open source technology platform and marketplace to help further democratize the hedge fund industry. QuantInsti will be offering training sessions within their executive training curriculum to allow students to gain practical skills using Quantiacs open source tools and data. Quantiacs experts will be joining QuantInsti's faculty team for its executive program in algorithmic trading. Now, to know more, definitely there's a lot more that can be spoken about Quantiacs, and who better to talk about it than today's speaker, that is Mr. Eric Hamer. Now, Mr. Eric Hamer is the CTO of Quantiacs. He's a serial entrepreneur with degrees in physics and computer science. Eric's experience includes machine learning, cloud computing, and Python programming. Before joining Quantiacs, Eric was the founding CTO at NetInformer, a mobile media company whose customers included Major League Baseball, the NCAA, and Verizon Wireless. Prior to NetInformer, Eric worked at Keynote Systems, where he invented their patented transactive perspective, which measured and monitored the performance of the internet. Apart from this, Eric's hobby is options trading, so he is a live trader as well. And I believe we do have Eric on the line right now. Just let me get him here for you. Great. So Eric is online. Eric, can you hear me clearly? Would you like to say a quick hello to the audience who have gathered here today to listen to your webinar?
No, I would certainly like to say hello, and I appreciate everyone from around the world joining us today. At Quantiacs, we are extremely excited about this partnership. We realize that worldwide there are many more people interested in becoming quantitative traders than there are employment opportunities. So any opportunity we have to promote quantitative trading, we will certainly do that. So again, we're extremely excited about this partnership. If you are not familiar with Quantiacs, let me just quickly introduce the company. Quantiacs is located here in Silicon Valley. We are the world's first crowdsourced hedge fund. For us, we have our quants develop algorithms, we connect it to capital, and the quant profits. We also have frequent competitions where anyone who is registered with has registered on our platform may submit as many strategies as they would like, and the top performing strategies win investment capital. And again, when this investment capital is traded against their strategies, if they profit, we split the profits with the quants, or we split a portion of the profits with the quants.
Great. Eric, so I'm going to give you the screen sharing rights right now. If you could share your screens as well, that would be great. And you can start with the webinar.
Again, Quantiacs is a Silicon Valley company. We are the world's first crowdsourced hedge funds. We For us, we have a community of quants. For us, our quants code algorithms, we attempt to connect it to capital. When that happens and the trading strategy is successful, both the Quant and Quantiacs profits. We also have frequent competitions that allow our quants to potentially win investment capital. We are extremely excited about this partnership with QuantInsti, as at Quantiacs we can see that there are many more individuals interested in doing quantitative trading than there are available employment opportunities. So any chance we have to promote quantitative trading, we certainly do it. At Quantiacs, to get started, we have a page dedicated just to that. We provide downloadable desktop toolkits in both MATLAB and Python. We provide sample trading strategies to get you started. For our quants, we provide end-of-day futures data going back to as early as 1990 or whenever that particular future started trading, whichever comes later. We like the futures markets. They're extremely liquid. They make it possible to establish long positions and short positions. There are no uptick rules or anything like that. So it's very easy to bet against the market as it is to bet in favor of the market. Most recently, we have added macroeconomic indicators. These are entities like GDP growth, employment numbers, inflation, payroll, and the like. These are assisting our quants in improving their algorithms. We also have an online platform where once you are satisfied with your algorithm, you submit it to our platform. We will evaluate it at the end of every trading day. And we will update your equity curve, update your performance, and the like. So all this is available free of charge to our quants. All that we do is ask that you register with a valid email address so we can provide you with updates to our system and updates on our competitions. But again, this is all, there's no charge to the quant. Our data is checked and rechecked, so we know that when you run a back test on any of your algorithms that you were using completely valid data. And at this point, we are working just with futures. That may, equities in the United States are extremely popular. Something I learned in the last couple of days, the Sharpe ratio, essentially the risk-adjusted performance of the S&P 500 is twice its long-term average. So the last few years have been extremely good ones for the stock market, and there is an extreme interest in equities. And again, over time, Quantiacs may provide comparable data for the equity markets as well. So what you see here, I'm actually going to bring this up full screen. Just bear with me. What you see here is a sample strategy. This strategy is quite simple. It goes long in the market when for a given futures, the 40-day moving average exceeds the 200-day moving average, and likewise it goes short when the 40-day moving average is less than the 200-day moving average. Now, and again, this is all accomplished in about 20 lines of code. So our toolkit is very, very simple to use. There are two key parts to the toolkit. For every algorithm, we have a My Settings area, and in this section, you specify what you are, you give us the basic settings that your algorithm needs. So in this case, it's telling us what futures it's following. It's telling us, with the look back, it is telling us how many days in the past do I need so that I can perform my analysis, train my machine learning algorithm, or what. The budget is just a hypothetical number for the initial value of this portfolio. We set it to $1 million as a default, but it could be anything. The slippage is essentially a transaction cost, so that we only deal, at this point, we only deal with end-of-day data. So you will run your algorithm, and then you will tell us what futures you're interested in either investing in or removing from your existing portfolio. And for each of those, there's a 5% cost, and that cost is based on the difference between the delta between the high price and the low price on the day you make your purchase. So this is our way of accounting for transaction costs, commissions, and the like. And this, using 5% of the delta, is a pretty consistent way of doing it. That way, if you're investing in a lot of extremely volatile entities, your costs are going to be slightly higher than if you were to invest in something that was had a lower volatility. So the second part of every trading strategy is this function called My Trading System. Here you tell our system what price information you need. So you'll always need to know the dates, but then you can request for a given day the open, high, low, close, and volume. We also can pass in things like, for futures, things like open interest. So we pass you this information for all the futures. You run your analysis and pass back to us a vector or a matrix with the weights of how you want your portfolio weighted. We then take that and make the relevant transactions and update your portfolio. This is all done on a hypothetical basis at the end of every business day. For our quants, where we actually have capital associated with their algorithm, whatever is specified in this new weights vector would lead to specific transactions taking place, either buying or selling, and the like. We discourage our quants from using any global variables. We don't want to risk there being any kind of namespace collision. So one of the parameters that you can pass back to us is your settings, if you need, which is just a simple Python dictionary. If you need to maintain any state information, put it in the settings, and that way the next time we call you, we pass you back your settings so you can pull that information out. Again, so this may look somewhat cryptic, but if you do register and download the toolkit, it really does start to make sense. So with two simple functions and less than 50 lines of code, I've coded an algorithm. Okay, so now what I'd like to do is actually take a look at the output of this algorithm. This is what our Python toolkit produces. So you can see the key part of it is the equity curve, how this simple trading strategy has done over time. We can see that it's returned 2.5% per year, which again is not great, but it certainly isn't losing anything. So for a start, that's pretty good. We are also show you how it moves between long and short positions. We can take a look at how just the long positions have performed. We can take a look at how just the short positions have performed. We can also zero in on how each of the individual futures that we have selected to invest in have performed. So here we can see that soybeans have not done particularly well. As a point of comparison, I can also bring up exactly what the soybean futures have done in this same time frame. So we can see that obviously for this time period, this is not a futures that has done well at all. Okay. So what do we look for when a strategy is evaluated? Obviously, we want positive performance. I mean, the whole purpose here is to make money. Good performance with low volatility is the most desired. Again, the primary number that our potential investors look at, and the number that we use to determine the winners of the programming contest, is the Sharpe ratio. This is just, the Sharpe ratio essentially gives you what your risk-adjusted returns are. Obviously, if a portfolio only requires $10,000 to make an additional $1,000, that's much better than a comparable portfolio that would require $100,000 to make an additional $1,000. So the Sharpe ratio gives us a look at what the risk-adjusted return is. We have seen that strategies with a lot of churn that go in and out of the market tend not to do well. Again, because every time there's a transaction, there is associated transaction costs. There will be commissions, and you're not always guaranteed to get the exact price that you like. So again, the Sharpe ratio is what we look at. The risk, we're really looking for trading strategies that maximize the risk-adjusted return and do so without a lot of churning. Now, machine learning. As I'm sure everyone in this webinar is aware, this is a really hot topic in quantitative finance. It is estimated that 85% of the trades that take place on the American stock exchanges or American exchanges are computer generated. I actually read a brief tweet yesterday saying that this number may be as high as 90%, that only 10% of trades are done based on the work of an analyst. So everything is computer generated. The good news is both MATLAB and Python have very strong support for machine learning. There are, as you will see, Python has many open source libraries that can be downloaded and used for free. So the time to do artificial intelligence and quantitative finance is definitely now. So a few machine learning techniques. If you're using regression, typically you are trying to come up with a way of predicting continuous values. You could consider this to be an advanced way of doing curve fitting. Classification is similar, where you are taking discrete entities and trying to categorize them. Clustering is a technique that is very common machine learning technique when you have unstructured data, where you're just provided a bunch of data and you don't know what the potential connections are. For clustering, you essentially assign values and see which nodes your data clusters around, and constantly recalculate that to see how your data is best divided. All of these techniques can be done with the scikit Python package. Again, this is open source. It's available for free. The one scikit does within the Python realm, scikit does an extremely good job of providing support for machine learning. The only drawback is, I believe, all their libraries only work on traditional CPU architectures, not the more high-performance GPU architectures. But maybe over time that will change. Another big one in machine learning is the notion of neural networks. This is quickly becoming extremely popular in artificial intelligence. I mean, the kind of neat part of a neural network is the fundamental unit of the neural network is a perceptron, and this is extremely is analogous to a biological neuron in that both of them accept inputs and both of them fire off some kind of signal to the next layer. So we're saying that a neural network is comparable to the human brain, or at least analogous to the human brain. There is some substance there. The neural networks use a layered architecture. There's typically an input layer, an output layer, and a set of one or more hidden layers in between the two. The good news with neural networks are when set up and trained correctly, you can get extremely good results. One of the downsides are the runtimes can be extremely lengthy with a traditional CPU. I mean, just imagine, a matrix of nodes, each one can communicate to all the others. You can see that just the cross products and the number of calculations is going to be extremely high. The good news is there are libraries that will work on the much more high-performing GPUs, and that can cut down the execution time by up to a factor of 25. So how do we take machine learning and apply it to any kind of problem, including quantitative finance? One thing I would like to say, I've noticed with our quants, a lot of them come in thinking that, oh, I can just throw together, a machine learning algorithm and have, best-in-breed investment returns. It's not the case at all. This is a complicated process. It's not trivial. It's not, something that you can just, spend an afternoon and all of a sudden have, a top-tier algorithm. It does take work. It takes, trying things, retrying things, but as you'll see, when it does work, it works quite well. So the whole machine learning process, obviously the starting point is specifying the problem statement. What exactly are you trying to do? And as you'll see in a few slides, we're going to attempt to predict the returns of specific futures. So again, is this once you've essentially specified or stated your problem, identify what kind of machine learning problem is it? Are you trying to classify something? Are you trying to predict something? Are you trying to do a regression on a bunch of data points? Once you've decided that, in our case, it's actually will be a prediction problem. One thing about machine learning is everything must be numeric. If you are working on a problem where, let's say you're trying to take inputs on characteristics of a flower and predict the color, that's a perfectly legitimate artificial intelligence problem, but you need to make sure that you've come up with some way of encoding how you identify your colors in a numerical matrix. And there's quite a bit of documentation on one-shot encoding and the like, but for machine learning, everything needs to be numeric. Once you've identified your data set and made sure that everything is in numerical format, you typically take the data set and divide it into training data which is used to make your machine learning model learn, and then test data which is used to run against the trained model to see how well it performs. So again, the training data is used to teach the algorithm. The test data is used to see how well the trained algorithm performs. Typically, for a given data set, anywhere from 60 to 80% can be used for training data, and the rest is used to test it. And again, your specific requirements will most likely dictate something in that range. So in this case, what we're going to do is we're going to attempt to predict the mini S&P 500 futures. The symbol there is ES. The mini S&P future, there is an S&P futures out there, and at the current value of the S&P 500, buying one S&P 500 contract would cost more than $120,000. So to make it more palatable, they've come up with what they call the mini S&P 500, which is just a single contract is a fifth of that. So it's at this point less than $25,000. So what we will do is we will use the toolkit that comes with the Python Quantiacs Python application, use it to load the data. We'll split it into training and test data. We will format the data in a correct matrix format. We'll create the machine learning engine. We will take the training data to fit the model, and then we will take our live data and see how well our machine learning algorithm is done. We will then display the results. In this particular case, we are using the Keras neural network API. This is, again, open source. It is available for Python. It's, all things considered, a relatively simple neural network to program to. It uses a sequential model, so you basically add the layers you need. In our particular instance, we'll be using just a single hidden layer neural network, mainly to save on computing time. But this is a very powerful package. As you'll see, there are lots of parameters, default values, and the like that you can specify, so take a close look at it. The good news is that it will run both. There is a CPU version and a GPU version, so if you're fortunate enough to have access to GPU architecture, you can run it there. And again, it's open source, so there is no cost. So when I create this simple model and attempt to predict the S&P 500, I basically give my model the history of the S&P 500 and say predict tomorrow. And if you look at first glance, it actually looks pretty good. The blue is the actual data for this period of about 2014 to 2017, and the red is what the model predicts. Now, again, at first look, it's pretty good. You can see that clearly it's a little bit, my model is under-predicting it, but most of the big peaks and valleys are there. The reality is it's not that good at all. That really, the network, there's so much financial data and so much noisy data that I'm passing it that basically the model says the best prediction for tomorrow is today. So if you look, the red is almost just shifted one day to the right of the blue data. So while this may look extremely good, if you look under the covers, it really isn't. If we apply the exact same algorithm as opposed to the raw data to the returns, so essentially today's price divided by yesterday's price to give the return, we can see something similar that one, the true returns are quite volatile. They're all over the place, but the predicted tend to follow the same shape, but not nearly the same magnitude. And again, that is something that needs to be addressed. But you can, if you really look under the covers, you will see that the algorithm is really just using today's data as a proxy for what tomorrow's data should be. So again, for the actual true values, it appeared that our network closely matched the actual data. For the returns, the data was not nearly as good, that the actual data was much more volatile than the predicted data. And again, both sets had less magnitude. So that really raises the question, is this an avenue we should approach? We should go down, but we will. So what we'll do now is we will combine this simple one-layer neural network that we've created and attempt to predict the future of the same mini S&P futures. So again, we will take 2 years worth of data, train the network, and print out and see how we've done. And again, if you look here, this is the output. We'll look at the source code in a second. This is the output, and this is done horribly. This, returns are negative. This certainly hasn't worked. Before we go into more analysis of this, let's jump and take a look at what the actual source code looks like, so you can get a feel for how this works. Bear with me a second. So here, similar to the what I showed in the first toolkit example, I have my trading function, my trading system function that that is called with each day's worth of data. What I do is look to see the first time, when it's called, I look to see, have I added a model, my neural network model, to the settings? And if I haven't, I basically take my look back data and train my model with it. And the training, so with the training, I basically, I've asked for 2 years worth of data. My look back is set to 504 days, which is approximately, in terms of business days, that's approximately 2 years worth of data. I have my pricing data. I calculate, so when I run my analysis, I normalize my data. Essentially, I subtract the average, divide by standard deviation. So I have my price data. I create, I have my price data, and I have the return data, which is essentially, today's price divided by yesterday's price. So I want to use my price data to predict my return data. So I create both of these sets. And again, I'm not, the first time this is called, I'm given 2 years of look back data. That will be used to train my network. Once my network is trained, the toolkit will call my my function with each new day's set of data, and I will use that to attempt to predict what the S&P 500 does. So I'm creating a sequential Keras model. And sequential just means that I'm going to start with a bare bones model and add the specific layers I need. I then add my input layer, which has an input dimension of 1. We're basically passing it price data. I add a single hidden layer. I then tell it that as it's modeling, I want to, the loss function should be mean squared error, and the optimizer should be ADAM, which is adaptive moment estimation. It's just one way of how do I optimize the process. So I then tell the model to go ahead and fit the data I have. So the training data is the actual price data. The X values of the training data is the price data. The Y values are the return data that are what I hoped to predict when we go to the future. I then put all this information into my settings, so each time I'm given a new day's worth of data, I can pull what I need out of my settings to perform my analysis. So the first time my trading system was called, I trained my model. Then for each new time it is called, with data moving forward, I'm able to essentially pull my model out of the settings, take a look at the most recent data, so I have the daily close, and use my model now to predict what the returns will be based on my model. From that information, I then decide whether or not to go long or short in this particular market. In this case, there's just one future, is the S&P 500. And again, after I make my decision of whether to go long or short, I pass it back to the toolkit, which does this evaluation, and then turns around and passes me the next day's worth of data. So again, in significantly less than 100 lines of code, I've created a neural network to analyze financial data. I agree that it does not do particularly well, but that becomes the next issue. So again, I've used a neural network to predict the S&P mini futures. It has not done well at all. So again, the results are poor. We certainly couldn't use these to trade by any stretch of the imagination, but at the same time, this algorithm used just the closing price. It made no attempt to look at any relationships between the high, low, and close on a daily basis, or to look at the volume or open interest. So a lot more could be done. I also took just raw data where perhaps if I had used something like moving average, momentum, relative strength, any of the standard financial indicators, maybe I would have had better luck. Just to show that this problem is solvable, what we are looking at here is an actual algorithm submitted by one of our quants. And as you can see, this is done extremely, his fitting is extremely good historically. And while you really can't tell, this light blue part is its performance with live data. This particular algorithm has done quite well on live data. So this problem clearly is solvable. My simple S&P 500 mini model did not work, but with the right effort, you can certainly apply these machine learning techniques and come up with very, very successful strategies. One last piece on machine learning, in addition to the techniques that we talked about, regression, classification, and the like, once you have those in place, there are ways that you can further optimize them. Gradient descent is a very popular method. If you have a clearly defined cost function, gradient descent applies simple calculus techniques, mainly looking at the first derivative to zero in on where are my minima or maxima, depending on what you're looking at. That's a very powerful tool. There's a notion of boosting, where constantly looking at your weakest data points and seeing what can I do to increase their validity, to make to make them more recognizable. There's another technique called bootstrap aggregating, or they call it bagging for short, where essentially you chop up your data in different ways and run your algorithms and see what you can learn from that. These are very common techniques, and all of them have comparable open source Python libraries that will help you do that. So a few things that I have learned personally, and I believe our quants would be the first to tell you, when applying machine learning to quantitative finance, simple strategies tend to perform better. Keep it simple. If possible, consider using multiple predictions and apply them and attempt to reach a consensus. Use a voting kind of thing. Sometimes, if the raw data is noisy or encompasses a broad range, replace it with features. So if you're looking at, as an example, if you're looking at the returns of an investment, as opposed to saying, I want this algorithm to predict the return, say, I want this algorithm to do its best to predict, will this return between -1% and 1%, or 1% and 2%, or 2% and 5%, categorize things as opposed to coming up with a specific numerical value. If you do work hard and you are creative, it will be rewarded. Our best quants, you do some really neat things with machine learning and come up with very, very strong performing algorithms. A few things to watch for. Unequivocally, the biggest one is overfitting. Anyone who has studied any amount of math knows that if you're given n data points, you can always find an n-1 degree polynomial that will fit all of them. That's great. That's academic. When it comes to running that against live data, it will not work well at all. So again, overfitting is just the one thing that will make will destroy your algorithms. Again, keep it simple. Don't overfit. Likewise, make sure your data is clean. Make sure that on the one hand, there's nothing in your data where the high and low are flipped, where or any anomalies like that. Also, if you're working with missing data, which we do at Quantiacs, some of the different futures have come into existence at different times. So we have missing earlier data. Make sure that is treated consistently. Don't do anything. Don't make any assumptions about your prior data that could affect the outcome of your algorithms. Also, finally, be careful if you introduce any random variables in your code. Make sure that they are accounted for as, if we see an algorithm and we run it twice and the outputs are different, that's disqualified from it's disqualified from all our competitions and probably would never be invested in. So make sure that your output is consistent run to run, and looking at possibly the use of random variables is something that you would need to address there. So again, summarizing, there's absolutely no doubt that machine learning and artificial intelligence are going to be key tools in forecasting the financial markets. I mean, it's certainly headed that way. I believe about a month ago, BlackRock, one of the biggest investment banks in the United States, said that they were that they were going to sharply cut back the number of analysts they use and use machine learning instead. So now is certainly the time. The tools are absolutely in place to make these algorithms possible. And again, as we have seen, when used properly, they can come up with really great trading strategies. So again, I hope you found this useful. Please visit us at Quantiacs. If you would like to download the toolkit in either language, MATLAB or Python, you will need to register, but I would encourage you to do it. We have a great support network, some neat quants, and we have very frequent competitions where the winners do get investment capital.
Great. Wow, Eric, that was a fantastic presentation, and I'm sure all the others would agree with me as well. And once again, thank you so much for your time. I will open the round for some questions in a couple of minutes. In the meanwhile, for all the people who are attending, here's the page with the details of the GitHub link. Right, give me a moment. Great. So if you see here, you've got some sample Python trading strategies on the Quantiacs GitHub page, some source code, and once again, here's the additional information for Quantiacs. Make sure you do visit that page. I just wanted to take a minute to talk to you guys about EPAT and Quantra, which is a course offered by QuantInsti. Now, the executive program in algo trading, that's EPAT, is designed for professionals looking to grow in the field or planning to start their careers in the algo or the quant trading field. The EPAT program includes dedicated sessions on machine learning. Covered under machine learning in EPAT is linear regression, logistic regression, GAM, LDA, touch upon wavelets, trees, ensemble methods, neural nets, SVM, deep learning, feature selection, potential pitfalls, along with trading strategy examples and implementable codes. The Quantiacs domain experts will be joining the faculty team, as I had mentioned earlier, and they will cover machine learning sessions using Quantiacs platform. For those who are looking for a self-paced course, we also have trading with machine learning regression on Quantra, wherein you can learn how to use machine learning in a step-by-step way, implementing regression technique using machine learning, using Python, while doing lots of guided hands-on coding, learning how to interpret predictions and using them to generate trade signals, and understanding and resolving bias. You would also get downloadable strategy codes and lifetime access to the course contents. Now, talking about EPAT, we would be commencing our 35th batch from 29 July. We've covered more than 50 countries with EPAT, and due to the popularity, success, and the fees would be going a little bit higher from the 36th batch, which starts in October. We do have an ever-evolving curriculum, so that makes it more of something that you want to learn. So if you think this is of interest, get in touch with us and save some money. Take the next step in your career of algorithmic trading. Eric, I'll be handing over the mic to you once again, and you can take some questions that have been asked by our attendees. So we've got Roshan here who's asked machine learning with R or Python, which one would be better?
That's a very good question. I would say they're both good. I mean, R is a statistics-based language. They're both good. I don't know for a fact, but you might find that there are more libraries available for Python. But again, both are very, very good languages and well suited to the task. So my guess is you would have good luck with both.
All right, that's great. Also, we've got a question here by Aditya. How do we check the predictive power of features or alternative data sets and avoid overfit using machine learning?
Okay, that's a very good question. Overfitting is definitely the bugaboo of machine learning. What you can do is a few things you can do when you after you've trained your model with whatever, whether it's neural networks or scikit or whatever. Once you've trained it, Pat, see how it predicts your test data. Generate, look at what you come up with some notion of an error function. A trick you can do is take your training data after you fitted the model and see what it predicts on your training data, and if it's very accurately predicting your trading data, but not your live data, you've probably overfitted. If the kind of error between the two is similar, you might have a better, a less overfitted algorithm. But overfitting is definitely the real pitfall of machine learning. I mean, if you come up with some model and when you start putting your test data into it, it doesn't, it's not the least bit accurate. You've probably overfitted. You've probably got something that's very good on your test data, but not really good for, that probably is not going to do well when it has to take on live data. Another trick is the idea of the bootstrapped aggregation, the bagging, where if you have a data set of 1,000 points, come up with 10 different sets of training data of 100 points each, and see how each of those do. That may give you an idea as well. But I mean,
I think, Eric, I guess that pretty much summarizes the pitfall of overfitting in machine learning. We have a very small question here. What is the general accuracy percentage of the machine learning model for algo trading?
Boy, that's a really good question.
In your experience, what would be the general accuracy?
I mean, I would say, I mean, it really varies. I mean, anything over 50% is probably going to be good. I mean, obviously you'd like it to be, closer to, 90 or 100%, but anything over 50% is probably going to be good. The downside here is financial data is extremely noisy. There's lots of, fluctuations. When you look at the fluctuations in the returns of the S&P 500, it's hard to fathom that all those widely varying returns over time have produced something that makes year over year tends to has historically done well. But I would say north of 50%, you're in pretty good shape.
Great. Well, Eric, I would be taking over the mic once again. Thank you so much for answering all of the questions that were asked today. For our attendees, a recording will be available once it has been uploaded. And Eric, thank you so much for taking time out to take this wonderful webinar today. And I hope you have a great day ahead.
All right, great. Thank you very much. This has been entirely my pleasure. Thank you.
Great. Thanks so much for your time, Eric. And to our attendees, once again, just would like to share our contact details. Just as a quick reminder, the EPAT batch number 35 starts on July 29, 2017. We do have the early bird discounts going on till 20th of June. And post this batch, from the 36th batch, there would be a price hike due to the ever-evolving curriculum, popularity, and the success stories. And also, if you're looking for a self-paced course, we do have Trading with Machine Learning Regression that's available on Quantra, and something that is applicable till 17th June midnight GMT. You can use a coupon code MLWEB20 to avail 20% off on the course. I hope you guys had a wonderful webinar, and thank you for taking time out from all of your busy schedules to attend this webinar. And I hope all of you guys have a great day ahead. The recording will be sent to you. The link will be sent to you via email once the recording has been uploaded. And the email would be sent to the registered email ID that you have used to log into the webinar. Thank you so much for your time, and have a wonderful day ahead. Bye-bye.
Well, algorithmic trading requires you to merge two traditionally disjoint set of skills. One is finance, another is technology. So you need to merge skills in finance and technology to be able to do algorithmic trading. So you need to understand the markets, you need to understand big data statistics to be able to design your strategies. But once you have designed the strategies, you need to also understand technology to be able to automate your strategies. So therefore, that is where the QuantInsti's education programs come into place. So we train people about the entire gamut of operations and skills required to be able to be a successful algorithmic trader.